Okay, hello everyone. Shall we start? We welcome to the ninth year of our summer school. It's time flies. So this summer we have the pleasure to invite Dr. Ting-Wei Chao from MIT to tell us something about entropy and how to use it in extremal combinatorics. Ting-Wei has done some excellent work in extremal graph theory and also discrete geometry. So it's all yours.
Thank you, Hong, and thank you for getting me here. And I'm going to tell you something about entropy and mainly focus on how to use entropy in combinatorics problem, especially extremal combinatorics problem. And the main purpose, I want to make sure everyone understands most of the things. So if you feel like you don't understand what I'm saying, feel free to stop me and ask questions. So let's get started. So the notion of entropy we are going to use throughout this course is called the Shannon entropy, and it is introduced by Shannon in order to talk about encode how many bits you need to encode, say, a random variable. So maybe let's start with a definition, and then I will talk about the motivation of Shannon's. So before start talking about entropy, I would like to define what is the support of a random variable. So let's say x is a random variable. And here we always assume our random variable are discrete. The support of x is just defined to be all the possible element x, such that the probability of hitting this x is non-zero, is positive. So here the notation is Px of x is the probability that the capital X, the random variable, hits this element x. So with this definition, we can define a Shannon entropy, which is given by you sum over all the possible outcomes, you sum negative p log p. So let me write it down. So again, x is a random variable, and throughout this course, we will assume all the random variables has finite support. Which means that you look at its support, the size of the support is finite. So that means this. And the entropy of x is given by you sum over all the x in the support, summing negative p of hitting this x times log of that. Here, this is lowercase x. And turns out it's quite useful in many situations. And roughly speaking, the entropy of x measures how many bits you need to encode the function, encode the random variable x. So you could think of this as how many information does this random variable x contains. And indeed, there is a formal statement by Shannon talking about the intuition I just said. And this is also the reason why this is studied. So let's say phi is a coding function. Of a random variable y. If phi is an injective map, mapping all the elements in support y to a 0, 1 bit, like 0, 1 string of arbitrary length. So if phi is a mapping from the support of y injectively to 0, 1 string with arbitrary length. And let's say for convenience, we define L to be the length of phi of y. So here y is a random variable, so phi of y will be a random outcome, so the length will be a random variable as well. And the theorem of Shannon says that if x1, if you have a random variable x, so you fix a random variable x and sample IID copies of x, you get x1, x2, to xn. And let's say phi is a coding function of x, of these, like this string of sequence, namely you want to do this resampling x many, many times, and you want to understand the expectation length of bits that you require to encode these string x1 to xn. So let's say phi is a coding function of x1 to xn. Then basically the length of this coding function will be given by the entropy of x. Namely, we have the following two statements. So the first part says that for any phi, for any function that encodes x1 to xn, the expected length is always at least n times h of x plus some lower order term, minus some lower order term. So basically it says that the first part of the statement says that phi is the lower bound. Like the entropy of x is the lower bound of number of bits. On average, you need to encode n copies of x. So here you see an n times h of x, meaning that roughly speaking, each copy requires h of x many bits to encode that. And there is a second part saying that this lower bound is essentially tight. So there exists a phi such that the expected length is upper bounded by n h of x plus little of n. So it basically says that the most efficient way to encode this random variable x n times is you need, anyways, you need n times h of x many bits. So on average, encode every copy of x, you need the entropy of x many bits. Okay, and let me give you a proof sketch, seeing how this p log negative p log p drops out from this definition, or from this theorem. So you could also think of this theorem as the definition of entropy, saying that the minimal possible number here you put here is the definition of entropy, and you can derive that it should be this function here. So let me give you a proof sketch. So maybe let's start with the case where y, let's say we want to encode just one random variable y and see how many bits do we need. So let's say if you have a random variable y, which is uniform, so let's say it is uniform on 1 through k, on k elements, sorry, in my notes I said r, on r elements, then you could expect that if I want to encode r bits, like r things uniformly, the length I need will be roughly log r, where log is in base 2, because you could always encode that using 0, 1 bits uniformly, and there are if you use x bit, there are 2 to the x many different outcomes, so you could squeeze these 1 through r in there as long as r is less than or equal to 2 to the x, so you might expect you need log r many bits. So you can easily prove that the expected length is log 2r minus 2. And this minus 2 comes from, you can also encode using shorter code words. So you could encode, say, the first element 1 into the code word 0, and the second element into the code word 1, and then 3 into 1, 0, 1, and 4 into, say, 1, 0, and so on. Okay, and the second part is that there exists a phi such that this is almost tight. And this part is quite easy to prove, so I'll leave it as an exercise. And instead, I want to talk about why the log comes up and talking about general random variable x. So let's say if you have a general random variable x, and let's assume the support of x consists of k elements, call them x1 through xk. Remember, our goal is to give a mapping from xi, give each xi, assign them a code word, the 0, 1 binary string, and then try to minimize the expected number of length. So let's assume pi is the probability of x hitting xi. Then we know that if we're sampling this x n times, then in expectation, we are going to have the element x, then the number of j such that xj, if you sample the j's time, that hits the output xi. You're going to hit this xi roughly n times the probability many times, right? So this will be roughly n times pi. And indeed, you can prove some concentration result using using Azuma's inequality or any type of concentration result says that it will be the number of xi, the number of times xi appear will be really close to n times pi. So for the purpose of showing you why that formula comes out, I will just assume that you hit each xi exactly n times pi many times. So indeed you have, let me write it more formally, n times pi. Okay, so you know that x1 through xn is almost uniform. Where this almost is like a hand waving, you could prove it rigorously, but I'm not going to talk about those concentration inequality. But you know this is uniform on n choose n times p1 to n times p2 all the way to n times pk, many elements. Because if you look at the string, x1 through xn, you know there are going to be n times p1 many outcomes that is x1 and n times p2 outcomes that is x2. So roughly speaking, and you know by symmetry, every possible outcome shows up with the same probability. So you know that x1 to xn is uniform on all the permutation of np1 copies of x1 and np2 copies of x2 and so on. So the typical outcome will be concentrated on uniform outcome on these elements. So there are going to be this many elements. And by part one, we know that if you have a uniform distribution, the expected number of expected length, expected number of bits you need to encode, that will be the log of this guy. So it remains to just compute the log of this guy and see that it indeed gives you n times h of x, roughly that rate. So let's compute the log of n choose np1 to n all the way to npk. Okay, so what is this? We know this is binomial coefficient. The numerator will be n factorial, and the denominator you see np1 factorial, np2 factorial, and so on. So this is the same as log of n factorial minus the sum of log of npi factorial. So we just need to expand these and see what's going on. And or we need to approximate, we should think of n being super large. So we can use Stirling approximation to approximate these terms. And by Stirling approximation, we know that if you have k factorial, take the log, it is roughly k log k minus k log e plus little of k. Because in the usual Stirling approximation, you have k factorial is approximately k over e to the k times some poly k term, or it's indeed 1 over, I forgot, 2 pi k. Is there a 2?
Yes.
Anyways, this part is like lower order term. So you see this approximation here. So this is n log n minus n log e. And for this part, we're approximating and get npi log 2 of npi minus npi log e plus little of n. Right, so I'm just applying Stirling approximation to all of these terms. And you can see that since sum of pi is 1, so this term f inside the summation should cancel with this term. And you can also see that I can decompose this one into npi log 2 of n plus npi log 2 of pi. And this npi will sums up to this n log n. So these two terms cancels. So basically, it remains n times negative p, summation of negative pi log 2 of pi plus the lower order terms. And remember, this is our definition. Our definition of entropy is to take all the possible outcomes, possible x inside the support, and sum the probability negative p log p. Any question? No? Okay. So this is indeed n times h of x plus lower order term. So basically, it says that if you imagine all the outcomes are like uniform on these permutation of np1 many x1, np2 many x2, then you get the expected length is indeed this one, and you can use some concentration type inequality to show that this is a typical case and recover and prove this theorem fully. Any question? Okay, so you write down the remark I said in Word. So h of x measures the expected number of bits needed to encode x. Okay. So this is the motivation why the entropy is defined to be negative sum over negative p log p. So I guess in order to use these, I'm going to show you many nice properties of the entropy so that we can use these property later on and see how to apply those to combinatorial, like extremal combinatorics problems. So well, maybe let me also still leave the definition of entropy on the board and start talking about their properties. But before that, I'm going to define another notion of entropy called the conditional entropy. So let's say you have two random variables x and y. And here we're always assume they are discrete with finite support. So I'll just ignore them, not write it down. And So what is the conditional entropy? The conditional entropy basically is you should think of this as the additional amount of bits you need to express y if you already expressed x. Which one am I using? Okay, so if we are talking about the entropy of x given y, then it should be the number of bits you need to express x after you already learned what the random variable y is. That's the additional amount of bits you need to encode that. So one way to define that is to define that as the difference between, or the increment from knowing y to knowing both x and y. So that's one way of defining that. And there are two more equivalent definitions, and they will be useful later on. So let me write it down. So the first one is the expected number of entropy of x given y equals y. So here I'm going to take y, this lowercase y, to have the same law as the capital Y, and take the expectation and try to measure for each outcome of y, how many bits do I need to encode x, and then take the expectations. That'll be the conditional entropy as well. So this is 2. And there's another definition, which is similar to that sum of p log p, but this time we need to sum x and y in the support of the pair x and y. And I'm also still going to sum p log p roughly. Well, this is the third way of defining conditional entropy, and indeed we are going to prove that these three definitions are equivalent. So these three are the same expression. Okay, so let's split the proof into two parts. First, I'm going to tell you why the definition 1 is equivalent to definition 3, and later I'm going to tell you why 2 is equivalent to 3. So let's first prove that 1 is the same as 3. So remember, the entropy of y is given by you sum over all possible y, negative py of y times log of py of y. And you can express this a little bit technically by extending that to sum over x and y. P of xy of y log py of y. Sorry, this should be x and y. Because if if I first sum over all x, summing this term will indeed give you py of y. So these are the same expression. And you can see this is quite close to part 3, except I need to, only need to change something inside the log, and that will indeed be given by the other term. Remember, the conditional entropy is defined to be a difference between entropy of xy minus the entropy of y. So let's also express this one. So for this one, by the definition, we are indeed summing over all possible pairs xy in the support. So this is negative pxy, xy, log 2 of p of xy, pxy of lowercase xy.
Sorry, why the second equality node?
Sorry?
So why the second equality node?
Second one, this one.
Uh-huh.
So here I'm just if you sum over all the x, then p of xy will be this one.
Okay.
So I'm just saying sum over x, the probability p of x being x and y being y will give you indeed the probability of just y equals y. Yeah, and all the other things doesn't change, right? So I'm just summing the first part. Okay, so you can look at the difference between this term and this term, and you know the difference between log is the division. So you know, h of xy minus h of x is indeed sum over xy, negative pxy of xy log 2 of. So I'm taking this term minus this term, so I'm going to take this one divided by this one.
You want the y there, right? On the left side of the equation.
Oh, thank you. Great. I want to take this one divided by this one. And that's indeed a formula in part 3. And actually, the main usage of this conditional entropy will either need the definition 1 or definition 2. Definition 3 is kind of just the intermediate step proving 1 equals 2. So next step, I'm going to show you why 2 equals 3. And this is also quite simple. You just try to expand everything. So node 3 is the same as, I can sum over xy. And I'm going to technically multiply by py of y and divide it back. And put pxy on top. And inside I have this log 2 of pxy of xy over py of y. And by writing the terms in this way, you can see that this one, and maybe let me sneak this negative inside. This one is indeed of the form like an entropy. And so, and indeed, you know that pxy, so you know pxy of xy over py of y. This is the marginal distribution of x condition y equals y, right? So this is the law of x given capital Y equals lowercase y. So this part indeed gives you the entropy of x condition y equals y. This is summing over y, dy of y. And you move sum over x inside, that will give you the entropy of x given y equals y. All right. So this is indeed just the expectation. So that shows you 2 is also equivalent to 3. Okay. So with all these definitions, maybe let me some board about this. Right. Okay, so let's start talking about the properties of entropies. So the first one is the, why do I write chain rule first? Okay, let's talk about chain rule. So in the conditional entropy, we see the relation, like the conditional entropy between 2 variables. And you could think of this like additional entropy, additional information is given by the increment. And you can do this like telescope sum to n variables. And that will indeed give you the chain rule, which says that if you have x1 through xn, then it is the same as computing the entropy of x1 given x2 to xn plus the entropy of x2 condition x3 to xn and so on, all the way to the entropy of just xn itself. And indeed, this follows quite easily from the definition of conditional entropy, right? Like, because this is the difference between all the n variables minus the entropy of the less n minus 1 variables. And the next term will be the entropy of the less n minus 1 variables minus the entropy of less n minus 2 variables. So the middle term will essentially get killed out, and all the terms will cancel, and only the first term remains. And this will be indeed quite useful if you are trying to compute the entropy of many random variables. we usually just break it using conditional entropy into like term by term and try to control like upper bound each term or try to play with each term. And the second proposition is the non-negativity. This is quite trivial. But this is also important. So we know that the entropy is always non-negative, because you can look at this definition here. P is always less than or equal to 1. And so log P is always negative, and you take a negative sign, so it's always not like positive, unless P equals 0, or I guess in that case we didn't sum them indeed. And since we know that the conditional entropy is the expectation of some entropy terms, so this will also be non-zero, so non-negative. So we know all the entropy terms are non-negative. Okay, and the next one is I will say the most important property, which helps us to connect entropy with like real, like counting objects, like counting combinatorics objects, which is the uniform bound. It basically says that the entropy of X is always upper bounded by log of the support size of X. And the equality holds if and only if X is uniform. And this indeed helps us to pass from like the world of computing entropy to the world of computing some real, like some combinatorial objects. Because if you know we have some like combinatorics object we want to estimate, we can try to sample that uniformly at random, and the equality holds. So the entropy of that random variable you sample uniformly at random will be exactly log of the size of whatever you want to count. And then you can play with this entropy and get some upper bound, and later you just upper bound all the entropic term by using this uniform bound again. So you can upper bound by some other like combinatorics objects, the number of that. So this is, I would say, one of the most important inequality about why entropy works for like extremal combinatorics. Okay, so let's prove it. Maybe let me take a spare board to prove that, so I can keep all the properties on one side. Okay. So we know the entropy is basically sum over p log negative p log p. So we want to look at the function negative p log p. And this is basically saying that we just need to show some concavity of the entropy, so that if the probability distribution is all the same for every outcome, then it maximizes the entropy. So basically, we want to understand the function negative p log p and show that it is concave. And indeed it is. By taking twice derivative or like any, like it's calculus. Okay, so you can apply Jensen. Remember, the entropy is given by negative p log p. So by Jensen's inequality, and let's also assume the support size is k. So here you are indeed summing over k terms. So you know by Jensen's inequality, you know this divided by k is upper bounded by, you take the average of these probability, and you know there are k terms, so the average is 1 over k. So this is negative 1 over k log 2 of 1 over k. Does that make sense? So basically, and just applying Jensen's inequality, there are k terms, so and since this function is concave, the maximum will happen at all the terms are the same. That will be exactly 1 over k for each term, so I get the right hand side. Okay, so we can rearrange terms. This is the entropy. And this is k, so we multiply by kq with this k. So this is less than or equal to negative log 1 over k, that is log k. So this is indeed the equality we want because k is defined to be the support size of x. And we also know that equality case holds for Jensen's inequality is that all the probabilities is a constant. Meaning that x is uniform. Okay, so this is the uniform bound. And for the next one, we have drop conditioning. So remember when I told you the conditional entropy, I talked about h of x given y is like an additional amount of bits you need to express x, given that you already like encoded y. But you can ask like, why can I not just ignore all the information from y and just encode x? So you know the amount of this information, the amount of bits you need to encode x given y, should be always upper bounded by the amount of bits you need to encode just x itself. So that's exactly the inequality given by we call dropping conditioning, which says that the conditional entropy x given y is always upper bounded by h of x. And the equality holds if and only if x and y are independent. So there are two independent random variables. That means you learn nothing after learning y. Learn nothing from x. And we also have a more conditional, more variable version of this, meaning that if there are conditional two variables, y and z, you can drop part of them. You can just drop the condition on y part. So this will be upper bounded by x given z. And here the equality holds case will be slightly more complicated. So this holds if and only if x and y are conditionally independent given z. So basically, this is the same as saying that if you look at the random variable x given z equals z, condition on any outcome of lowercase z, of like the random variable z, these are always independent. For any outcome z. Okay, so let's also try to prove that. So if you look at the conditional entropy h of x given y, by the formula 3, like this is, I guess this is the only time we need this, the third definition here. This is the same as sum over x and then sum over y. Py of y times negative pxy of xy over py of y. So here I'm also doing this technical, like multiply by py and divided by py trick. And log 2 of pxy of xy over py of y. This is remember this is one of the definition of the conditional entropy. And we can apply Jensen's inequality in a different way. So this time, remember this part is the expectation over y. And this is concave. So I can throw this guy inside, hitting these two parts. That will indeed give me some x. And I'm going to first pull this negative in front. So this one will hit the thing inside. So that will give you some y, py of y, and it's pxy of xy over py of y log the same thing. So here, this is an expectation, and I'm just using Jensen's to store inside hitting these two terms separately. But you know, this will cancel with this one, and this will cancel with this one. So inside, indeed, you get the entropy of sorry, this will cancels, and if you sum over y, that will indeed give you just px of x. So this is sum x negative px of x. So this term is the same as this term, this huge term here, and another log of px of x. This is h of x. Okay, so here's a little bit messy calculation, but I guess my point is that these can be proved using these convexity and like maybe just a calculus exercise. And we can also talk about the equality case. So the equality case here says that the equality case here basically says that this should be proportional to this one. So like, you know, this one equals this times this is the definition of being independent. So equality holds if and only if x and y are independent. And you can prove similarly, like by expanding everything, but if we already know the first line, we can prove the second line easily by using the second definition. So I'm going to just express the term h of x given yz into the expectation over z, the entropy of x given y and capital Z equals the outcome lowercase d, and apply the result from the first part. So we know we can drop conditioning, drop the whole condition here. This is the same as z, h of x given z equals d.
It's a Z, not an X.
Oh, thank you. And again, this is the entropy of x given z. And you can see from this equality, the equality case holds only if for every z in the support, for any possible outcome z, that the outcomes of x and the corresponding random variable x condition on z equals z and y condition on z equals z are independent by the equality case of the first part. And that is indeed like they are conditional independent. Okay, so this proves the drop conditioning. And okay, I think at some point I will need to erase all these boards. So I guess people are staring with this part for long enough. So there's a corollary. Remember, we have this drop conditioning, but you can also write this conditional entropy as using the first definition. So this is the same as the entropy of xy minus the entropy of y. And you can throw that copy of y to the right-hand side. That will give you the following corollary, saying that the entropy has some additivity. So basically, the intuition is still the same. If you want to express x and y, you want to use some bit to encode x and y, you can just encode them separately. And so the total entropy of x and y will be always upper bounded by the entropy of x plus the entropy of y. And equality is still the same. Equality holds if and only if they are independent. We also have this conditional version saying that if you have x and y but still condition z, it's upper bounded by h of x condition z plus h of y condition z. And equality holds again if x and y are conditionally independent given z. So far, so good. And okay, I guess for the second one, I write a little bit of proof because it might not be clear how you get from this one to this line. So let me just write it down.
I have a question.
Yes.
Since everything is due to the concave, the function of set concave.
Yes.
So why we rarely need this form minus x log 2x. Or whether we can translate this function.
Oh, you mean you want to replace that by any concave
Yeah,
function?
yeah.
I guess the main point is you need this uniform bound. I remember there are some like axioms saying that if you have a function satisfying uniform bound, drop it conditioning, and probably that's it, or like non-negativity, and I forgot doing anything else, but indeed satisfy all these axioms will indeed give you an entropy function up to a scaling. Yes, so that's a good question. So the entropy function is indeed like a special one that satisfies all these properties. Okay, maybe let me finish this proof. So for this one, you can again write it as using chain rule, you can write it as x condition y z plus entropy of y given z. And you drop the condition in the first part, you kill this. So this is h of x given z plus h of y given z. Okay, and there's another corollary from this one. So I can also write this as the difference between the entropy of x, y, z and the entropy of z, and also express the right hand side. So one copy of h of z will cancel, and that indeed gives you the entropy of x, y, z plus the entropy of z is less than or equal to the entropy of x, y, xz plus the entropy of yz. So this is called a submodularity. So entropy is indeed a submodular function. And submodularity basically is just saying it satisfies this equality here. So you should think of this as like you have a set of random variables and you have another set of random variables. You can always upper bound it by sorry, let me say that again. You have a set of random variables here and another set of random variables here. You can always lower bound it by their common intersection and their union. Okay, so that's submodularity. And there are also several propositions we will need about some deterministic function. Well, imagine that if I compose the random variable with a deterministic function, the amount of information I get should kind of collapse. So this, a list of propositions. Here I'm going to ignore all the like notation like domain codomain issue. I'm all like so you'll see I'm plugging x into f or like y into f or xy into f. But don't worry about that. I'm just saying for any deterministic function, the following holds. So the first one is that the entropy of f of x given x should be. Can anyone guess what it should be? if I already know the information from x, how many more bits I need to understand f of x?
0.
0. Yes. And I also have this. Let's say we already know x, and like we already know y, and we are spending some bits to understand x. Then we can get f of xy freely. So this is the same as the entropy of x given y. Because if you know x, you know y, and you spend some bits to understand x, this one you will get it for free. And we also have put in the function in the right-hand side version. So now if you already know y, you don't need anything to understand f of y. So this is the same as h of x given y. There are two more. So if you want to know, given y, know f of x, the amount of bit you need to spend will be less than or equal to knowing the full x. So this is less than or equal to the entropy of x given y. And this is indeed less than or equal to, if you only know part of y, so you should imagine like plugging y into a deterministic function is like knowing only part of that. You know less information. So this, if you start with knowing less information, then you need to spend probably more bits to understand x. So you have this inequality here. Okay, let's try to prove that. And bear with me, this will be the last proposition we are going to prove, and you'll start, after this, we'll start talking about how to apply these in combinatorics. So for the first one, like the equals 0 one, this is the same as the expectation of entropy of f of capital X, given capital X equals the outcome log small x. And this is the same as the expectation of small x, the entropy of, since you know capital X is small x, this is the same as f of small x. But this is just deterministic. This has only one outcome, so the entropy is 0. Okay, and for the second line, I want to show that x given x f of xy given y. We want to compute this guy. So we can use chain rule to break this term out. So this is the same as h of f of xy given xy plus h of x given y. So here I'm using chain rule. Remember, like, okay, chain rule also apply with when you are conditioning on something else. But here I'm just breaking this f of xy out. Like I'm breaking this condition on this, and versus just this term. So I get this one plus this one. And this one should be 0 from the first part, applying to the random variable, the tuple xy. So this is the same as this one, prove the second part. And for the third part, and do a similar trick. So for this one, I want to try to recover x given y. So I want to write this as a difference between h of x given y minus something. And by chain rule, this is x given y minus let me say that again. This is indeed x f of y given y minus h of f of y given y. Because if you apply chain rule, this term minus this term, you just move this one to the conditional side. That will give you this part. Or you could think of like I'm combining this term with this term, and the chain like connects this inside the condition with this one on the left hand side. So far, so good. So for this term, I can apply the result here. So f of y in particular is a deterministic function applying to x and y, but just ignoring x. So this is again 0. Did I mess up something? So not this one is 0. This one is h of xy. Because if we know x, know y, we get f of y for free by the second part, and this one by the first part is 0. So that proves the third part. And the fourth part and the fifth part are similar. We take h of f of x given y. You want to try to connect that with h of x given y. So I'm going to write this as h of knowing both x and f of x given y minus knowing h of x given y. So this is again the chain rule, right? So if you the chain rule. Is there something wrong on my note?
Choosing the additive.
This minus h of x given y and f of x, right? Yeah, if you add this term with this term, the chain rule will give you this term. And we know this term is always, like with the negative sign, this term is always negative. So the whole thing is less than or equal to just this term. But we know from the previous part, we can get this one for free. Okay, let's move on to the, so this is the left-hand side of 4, and we also have the right-hand side of 4. So we want to compute h of x given y. I can write it in terms as h of x given y and f of y. And just apply drop conditioning. This is this upper bounded by x given f of y. Okay, so I guess people are kind of familiar with all these operations with entropy and some of these properties. So before moving on to combinatorics problem, are there any questions? Okay, so let's talk about some combinatorial problems. So the first one is the bitwise information. The motivation problem question is quite simple. If I tell you you have a collection of sets. Let's say you have m sets, and there are on the ground set n. Such that, why am I writing this? Such that all the bits. So you could imagine these A1 to AN as the indicator vectors of like supported on n bits. And we want to understand, if I tell you all the bits are unbalanced, how large can my set be? So here, unbalanced means that, let's say, for any bit, it only appears in 1/3 of the sets here. or let's say the number of j indices of my sets that contains the element I is always 1/3 of my sets. And we want to ask how large can my collection of sets be? And indeed, the balance case is quite easy. If I instead asking you balance, if I replace this by equals m/2, you can simply just take all sets. So this problem is easy. But in order to, so it's kind of like if I told you some, like they are unbalanced, you learn some additional information about my sets. So the total size of total number of sets should be smaller. And we want to understand what's the asymptotic of that. So answer, let's start with constructions. So if I just take
By unbalanced, you mean inequality or equality?
Oh, here, in this setting, I want equality, but you can have some, you can derive a similar thing for like less than or equal to. I mean, equality will be easier to explain, but the method also works for inequality. Okay, so here's the construction. Let's say if n is divisible by 3, then I just pick the n/3 layer. So each element is expected to be hidden like one with probability 1/3. So every element is indeed lies in like 1/3 of the sets from here. So this is a construction, and we know that we can kind of lower bound it by this. So you can use the starting approximation and compute the binomial coefficients, and you know the size. The size is lower bounded by up to an extra factor, lower bounded by 2 to the h 1/3 of n, where h is the binary entropy. H of p is the same as the entropy of a Bernoulli random variable of probability p. That means I flip a coin, probability p will be head, 1 minus p will be tail, and compute the entropy. So this is the same as negative p log p minus 1 minus p log 1 minus p. And one natural question is that, is this construction tight or is this exponent tight? And turns out the answer is yes, you can prove this quite easily with entropy. And indeed, this leads us to the first way of applying entropy to combinatorial problem, meaning that you want to expose the bitwise information. If it's a bitwise information. So remember when we were talking about the uniform bound, we say that the only way to connect entropy with combinatorial object is to sample things uniformly at random. So let's say you have the family A1 to AN. I'm going to pick Xi to be the event. I'm going to pick X1 to Xn to be the indicator vector of AI, where the index I is chosen uniformly at random. So I'm going to pick one of them from A1 to AN, pick random, uniformly at random, pick one of them, and look at their indicator vector. That will be my like tuple X1 through Xn. So X1 through Xn are just like either 0 or 1, but with some randomness. And it's tied to these like indicator vectors of A1 to AN. And we know by the uniform bound, since we're picking that uniformly at random, this is the same as log m Okay, so we need to upper bound the entropy. And once we have a good upper bound of entropy, we can have an upper bound on M. And the most naive way is to just apply some additivity, because here we are given the information for each bit. For each bit, we have some information about. So, and each bit, like the ith bit will correspond to the variable xi here. So we should try to use some additivity to split all the bits. We know x1 through xn is upper bounded by h of x1 plus dot 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 to h of xn. Can anyone tell me what's the distribution of x1? Yes, it will be binomial 1/3, because you know only one, there is exactly 1/3 of sets that contains the first element, and in those sets you will see a 1 here, and otherwise you will see a 0. So x1 will be 1 with probability 1/3 and 0 with probability 2/3. Oh, this is indeed h of 1/3.
X and is log 2m.
This one?
Yeah.
Yes. So, like the only randomness here comes from I'm picking things from 1 to n. And okay, so here's one thing you need to be slightly careful. All these sets are different.
Yeah.
So all the indicator vectors are different. So you are in the uniform on m indicator vectors. So you have log m. Yes. And so back to here, each term gives you h of 1/3, you have n terms. So you get this. And if you combine that equality with this inequality, you get log 2 of m is less than or equal to h of 1/3 times n, which tells you that m is upper bounded by 2 to the h of 1/3 times n. Okay. And indeed, there is a quite interesting recent breakthrough. Also uses this idea. You want to try to look at the bitwise information of an indicator of some set of the sets, and then analyze like how much information you get by adding each bit. And indeed, Gilmer uses this to prove the union close conjecture up to a constant. So let me first state what is the union close conjecture and show you what Gilmer and the others did. So conjecture says that if you have a set family that is A1 through AM, supported on a ground set N, that is union closed, meaning that if you take any union, like union of any two sets in F, it is again in F. So union closed means that it is closed undertaking the operation union. And this holds for any I and J in my index N. And we want to say the union closed conjecture that there is a bit that is contained in the majority, like in at least half of the sets. And there exists an index I, or like an element I from my ground set, such that the number of sets that contains I is at least half of the sets. And turns out, like all these problems have a similar flavor that if you look at if you look at the indicator vector, it kind of tells you the bitwise information. So Gilmer indeed carried out this and quite surprisingly showed a quite nice and short, elegant entropic proof of this conjecture, but with this 1/2 replaced by 0.01. And that's quite a huge breakthrough because like before that, before Gilmer's, there are only proofs that the fraction depends on n. So let me state what they did. Okay, before that, let me tell you the construction. So this 1/2 is indeed tight. And by a dumb construction, you just take all the sets. And each I is in half of the sets, and it is union closed. So 1/2 is the best possible constant you could expect. Okay. So let me state the theorem by Gilmer. And later improved by many people. So there exists an I. So the setting is all the same. Like you have a set family F that is supported on n elements and it is union closed. And you want to ask what is the like can you find an I such that it lies in like C times n many fraction of the sets? There exists an I such that the number of sets that contains I is at least C times n. And Gilmer proved that this holds for C equals 0.01. And he didn't try to optimize his method. And in his paper, he said that by optimizing the method, the best one can hope is C equals 3 minus root 5 over 2, which is roughly 0.38. And the current best constant, using some more involved methods, we can show that this is roughly 0.38271. So it's like there's one day Gilmer posted this paper on arXiv, and later there are like 3 or 4 or 5 independent groups of people trying to push Gilmer's method to the best possible. Like he conjectured in his paper like this is the best possible limitation of his method, and people indeed achieve this in 1 weekend. And the next Monday or Tuesday on arXiv, there are like 3 or 4 papers about this. Okay, so I guess today I'm going to show you the idea of how to prove this one or this one. And the idea is quite simple. Like if you take two random like independent copies of uniform indicator vectors from the set family, like you know, if you take just one copy of uniform, one copy of indicate uniform. Okay, if you take one set from F uniformly at random, it should maximizes the entropy because you're taking uniformly at random. But if you take 2 copies of that and union them, and somehow if you are able to prove that after union, the entropy is larger, then you get a contradiction, right? Because you know the union is also supported on F, but so you know the union should have entropy upper bounded by just 1 copy of that. But on the other hand, if you can use these bitwise information analysis to prove the union has larger entropy, then you get a contradiction. Let's take uniformly at random. So by saying this, I'm trying to identify this as the indicator vectors. So you should think of this as x1 to xn and y1 to yn. So you have 2 indicator vectors. And you note that if you take x union y, this is another random set than an indicator vector, but this is also supported on F. So the entropy of X union Y should be smaller than the entropy of X by the uniform bound. And if you can use the bitwise information to show that, if you can show this, then you get a contradiction. Under the assumption that the union close conjecture doesn't hold for this C, if for any I, the number of sets J that contains I is less than Cn. So this is the contrapositive of the union close conjecture. If the union close conjecture hold, then one can use bitwise information to show that the inequality should get reversed and you get a contradiction. Okay, so let's see how is this executed. So for our convenience, let's define X less than I to be the collection of the initial segment, the first I minus 1 bits. And similarly, I will use the notation Y less than I or X union Y less than I similarly. But we can use chain rule to decompose the entropy of X union Y. Remember, X union Y is the tuple, so that in each bit, you just do the union among in each bit. So this is a tuple, like a tuple of n by n bits. So you can use chain rule to decompose these n bits. This is the same as sum from I equals 1 to n, h of X union Y, given I. Condition all the previous information, previous bits. Right? This is the chain rule. So I first tell you the I equals 1 bit, the first bit without condition on anything, and then tell you the second bit, condition on the first bit, and so on. Okay, so and we know that like we want to try to connect these terms with the information from X and Y, like independent, like separately. So I'm going to split this information into the information X less than I and Y less than I. And we know that this is a deterministic function of these two things. So by the like erased deterministic function property, this has smaller entropy. So this is lower bounded by this. And you can also expand h of X using chain rule as well. So this is sum from I equals 1 to n, h of Xi, condition X less than I. And one hope is that we want to compare this versus this term by term and showing that this is always larger than this one. Then we get a contradiction, we get the goal we want. Okay, we want to, oh, I missed a step. So we want to try to make things look nicer, and we know that X and Y are independent, so it's the same when you condition X less than I, and the same as you condition extra Y less than I. I'm going to write this. Because X and Y are independent, so it's no harm to just add this term. It's just the matter of matching the condition part. Okay, so our goal becomes we want to show bitwise this one is larger than this one. And So for convenience, let's set P and Q be two random variables. P will be the probability that xi equals 1, given x less than I and y less than I. And Q will be the probability that y equals 1, given the same thing. So these are random variables because, like, you know, there are randomness here, and for each outcome of x less than I, y less than I, that will give you a P and a Q. And for different outcomes, that will give you different P and different Q. So these two are random variables. Okay, so we can rewrite this one. You know, first rewrite the right-hand side. So the right-hand side is indeed the expectation of P. Sorry, h of P. Because for any outcome, you are seeing this xi, which is a Bernoulli random variable with probability P. That's a definition of P. So I'm just computing the binomial entropy of that. And so this will be the expectation of h of P. And on the left-hand side, I claim that this is the expectation of entropy of P plus Q minus PQ. The reason is that if you look at this P, if you look at the probability of this bit hitting P, this bit hitting I is P, and the probability of this bit hitting 1 is Q. So X union Y hits 1 if this or this happens. So the probability will be P plus Q minus P times Q, which will be a probability that both happen. So by inclusion exclusion, you need to subtract this term. Okay.
So should P and Q be 4?
Sorry?
Should P and Q be 4 plus S and Y are the same? No, almost same.
No, P and Q are random variables. So it's like if you fix one outcome of X and one outcome of Y, you get a pair of P and Q. So if the outcome of P and X and Y are different, you will get different P and different Q, like different P and Q. So the thing we want to show, this one, is equivalent to show that the expectation of h of P plus Q minus PQ is greater than or equal to the expectation of h of P. And indeed, we want some strict inequality, but this indeed happens in your first bit. So in the first bit, maybe let me first also reformulate the condition here. So I'm organized. Remember, we have this condition, and we kind of want to translate that into this language about P and Q. Remember the number of sets J that contains each element I, that contains this particular index I, is at most Cm. That means the number of the fraction of times where xi equals 1.
There's no little y, right? Only big y. Well, for the definition of Q.
Definition of Q. Thank you. Those are capital Y.
Just can small p and q are also random variables?
Yes, small p and q are random variables. Yeah, so this condition tells you that the expected number of times xi hit 1 is less than C. So the expectation of P is less than C. And we want to use this condition to prove this one. We can use this one to prove this one, then we are in a good shape. We show this, like this claim here, and that shows our goal. And indeed, we don't need to really worry too much about this one being strict inequality, because for I equals 1, we already get a strict inequality. So for I equals 1, we know we are conditioned on nothing. So P and Q are deterministic. They are just two numbers. And indeed, P will be equal to Q. So in this case, P equals Q, and they are both deterministic. And this calculation indeed becomes just computing h of 2p minus p squared, comparing with h of p, right? Because if you plug in p equals q, this gives you 2p minus p squared. So you are comparing these two, and this is indeed strict inequality if p less than c, which is the barrier 3 minus root 5 over 2. This is where we use this number. So when p equals 3 minus root 5 over 2, this is indeed equality. Okay, so we don't need to worry about that. We don't need to worry about strict inequality, so we only need to prove this inequality with this greater than or equal to. So what we want to show is that you have P and Q that follow some distribution mu, and they are independent. And we know the expectation of P is less than or equal to less than C. Can assume less than or equal to if we just want the non-strict inequality. Then the expectation of h of P plus Q minus PQ is greater than or equal to h of P. Oh, and PQ this is in 0, 1. And indeed, this is a easy exercise. If you discretize that, if you think about P and Q that only takes n values, discretize that, then this becomes an Olympiad inequality problem. So I will leave it as an exercise. But the hint is like you can do some like derivative and do some concavity argument. Be appear in your homework. And that's it for today. So tomorrow I'm going to tell you something more about graphs and like homomorphisms and etc.
So what would you say is the information F1 has a right to give? That all these words. So